Why is the concept of antimatter powering a Star Trek starship more of a sci-fi delusion than a real possibility? In Star Trek, antimatter is easy. You load antideuterium into the Enterprise warp core, stabilize it with a dilithium crystal, and blast off at warp 9.9. But in the real world, antimatter is an engineering nightmare. The problem with antimatter is that it doesn't exist naturally in any meaningful quantities. There are no antimatter planets, no giant reservoirs, and no lakes drifting through space waiting to be harvested. Our universe is made almost entirely of ordinary matter. If we want antimatter, there's only one way to get it. We have to create it. This is where the nightmare begins. One of the biggest fallacies in science fiction is that antimatter is treated like an oil well or coal mine, a natural source of energy just waiting to be harvested. The reality is, it isn't. Antimatter is an incredibly expensive and incredibly dangerous battery. To charge that battery, you first have to put energy into it. The laws of thermodynamics guarantee that you'll always have to put far more energy into creating antimatter than you'll ever get back. The energy payoff isn't X plus 1 or even break even. It's always X minus a massive loss. It would take an entire world the size of Jupiter just to create a single warp bubble for the USS Enterprise D. After decades of research, humanity has produced only microscopic quantities of antimatter. The estimated cost of producing just 1 gram is about $62.5 trillion. It is easily the most expensive substance humanity has ever produced. Captain Jean-Luc Picard's daily fuel bill would bankrupt our entire planet. But let's pretend money isn't an issue. To use antimatter as fuel, you have to answer a far more difficult question. How do you build a fuel tank for something that annihilates anything it touches? The instant an antiproton touches an ordinary atom, they annihilate each other in a flash of energy. Star Trek solves this with magnetic intermixed chambers, or what physics calls penning traps. Powerful magnetic and electrical fields suspend antimatter inside a near-perfect vacuum, preventing it from ever touching ordinary matter. What is humanity's record for storing antimatter? It's just over 16 minutes. But keeping antimatter contained also consumes energy, making an already terrible energy investment even worse. And what happens if the containment of antimatter fails? Science fiction may love dramatic warp core breaches, but reality is far less forgiving. If a magnetic containment field collapsed for even a microsecond, the resulting antimatter annihilation would release an enormous burst of gamma rays and high-energy particles moving outward at the speed of light. Matter and antimatter instantly annihilate each other, converting 100% of their mass directly into energy. An unimaginably intense flash of gamma radiation would slice through conventional shielding, destroy electronics, and deliver lethal doses of radiation instantly. Even if you had perfect containment for antimatter, it doesn't solve the engineering problem of heat. The more power your reactor produces, the more dangerous amount of waste heat it creates. When you're dealing with antimatter, even 1% waste heat represents a fatally destructive amount of energy. And in space, there is nowhere to dump all of that heat. In Star Trek, they simply dump it into subspace. But subspace is 100% fiction, invented by screenwriters. Cooling the antimatter reactor may become an even bigger engineering challenge than generating the power itself. If you try and use antimatter as an energy source, you'll never get more energy out than you put in. You'll never store it efficiently. You'll never contain it safely. And one tiny mistake ends in total annihilation. Science fiction treats antimatter as the ultimate fuel. Physics treats it as the ultimate engineering nightmare.